Hi everyone, this video is on composition of functions, where we learn a new way to construct a new function given two ingredient functions. So we already saw that we could combine two functions by addition, subtraction, multiplication, or division. Now we'll see that there's another operation that we can do instead. Consider these three functions. First one is h of x is the root of x squared plus 7, and the other two, f of x, x squared plus 7, and g of x, square root of x. What we want to do is to see how to create h of x using the other two. The way that we will do that is we'll start with g of x, which I'll copy it down. G of x is the square root of x. And then imagine plugging a letter into it. Like, I don't know, the letter f. What is g evaluated at f? So instead of the square root of x, there'll be the square root of f. Okay, not so bad. But what if f is something? What if f stands for something, like x squared plus 7? Well, now let's put in the x squared plus 7. But f of x is equal to x squared plus 7. I'm just not writing the bracket x there. So that'll be the square root of x squared plus 7. So what we did is we constructed h of x using these two ingredients, f of x and g of x. And we did it without multiplying f and g, or dividing f and g, or adding or subtracting f and g. We could have also done this in reverse order. We could have taken the function f of x and into it plugged g of x, and that would have created a different new function. The notation that the textbook uses, which is not a bad notation, not as good as another notation, but I'll show you it, is that it defines the composition that we just did as g circle f. You can also write it as a g circle f in brackets of x, which is not, that's even worse. A better notation, I think, more precise notation, is g evaluated at f of x. It means you're plugging f of x into g as if f of x was a number. But in actuality, for any x value, f of x is going to be a number as long as x is in the domain. Okay, and this new function is called the composite function. It's been composed of two ingredient functions, f of x and g of x. The order in which you do the composition will usually, but not always, change what the resulting function is. Another way of saying that is that g circle f is not necessarily the same thing as f circle g. To play a little bit with these compositions, here's an example. We're given two functions, f of x and g of x, and we're asked for the multiplication of the functions evaluated at 3, the division of the functions evaluated at 3, and the composition of the functions evaluated at 5. Let's see how that goes. So I'm going to split this up into 3 boxes. Maybe I'll do that. I'm trying to be organized here. There you go. All right. So the first box would be for A. So it says that h of x is f of x times g of x. So that's a small dot, not a composition. In the brackets it says to multiply. If it was a long problem, if it was worded properly, it would say product. Find the product f times g. Okay, so I'm going to put them side by side. F is 2x squared plus 3x. I'm putting brackets around it because the entire thing has been multiplied by g. And then g is x plus 1 over x minus 2. You can do a FOIL if you're desperate. I'm not desperate to FOIL and simplify and look for cancellations and all that stuff. I'm just going to do the next step of the calculation, which is to plug in 3 for x. So h of 3 is, replace all the x's with 3's. So 2 times 3 squared, so 2 times 9 plus 3 times 3, 9, times 3 plus 1, so 4 over 4 minus 2, which is 2. Now we can simplify. 2 times 9 is 18, plus 9 is 27, and 27 multiplied by 4 divided by 2, which is 2. So we get 54. Okay, that's our final answer. Part B. This time we're asked to divide f and g and then plug in 3. And there's a shortcut here that we could use, but oh, did I plug in? Oh, I messed up. Oops, I'm sorry. I messed that up. What is 3 minus 2? It is 1. So I have 27 times 4, which is 25 times 4 plus 2 times 4, 8. Okay. Okay. So the next one is just division. We have w of x. Is f divided by g. So 2x squared plus 3x all divided by x plus 1 over x minus 2. Double fraction, you can simplify it if you want. I'm not going to bother. I'm going to plug in 3. So I get 2 times 9 plus 9 over the double fraction 3 plus 1, 4, 3 minus 2, 1. And then simplify 2 times 9, 18, plus 9, 27. 4 divided by 1 is 4, so 27 over 4. Okay, that's it. And now the last one, the composition. So this is going to take a little bit more writing. P of x is f circle g, and I'm going to immediately convert that into f evaluated at g of x. It means the same thing. It's a different notation for composition. So f of x is 2x squared plus 3x, so this will be 2 times g squared plus 3g. All I did was I took the x's in f of x and replaced them by g's. And then I'm going to plug in what g is. So 2 times x plus 1 over x minus 2 all squared plus 3 times x plus 1 over x minus 2. Okay, now I'm going to evaluate that at 5. So 2 times 5 plus 1, 6. And then 5 minus 2, 3. All squared. Plus 3 times 5 plus 1, 6. X minus 2, 3. Okay, we'll simplify. 6 over 3 is 2. So I have 2 squared plus 3 times 2. So 2 times 4 plus 6. So 8 plus 6, which is 14. And then I'll circle all the final answers here. That's one way to do these things. The second way to do these things is to compute the ingredients at each of the x coordinates. So plug 3 into f of x and plug 3 into g of x. Then f multiplied by g at 3 is going to be f at 3 times g of 3, which is going to give us the same answer we have here. W at 3 is going to be f of 3 divided by g at 3, which is again going to be the same answer we have here, which is that's a 27. Looks like a 21. I better fix that circle. And then the last one is really where the time savings can be found. What is f of g evaluated at 5? What we could have done is we could have plugged 5 into g first. So let's do it quick. G of 5 is 5 plus 1, 6, divided by 5 minus 2, 3. 6 divided by 3 is 2. And then taken that output and plugged it into f of x. So what is f evaluated at 2? And we'd get the same answer, 14. I invite you to do that on your own and confirm that this is a safe type of procedure. All right, next example is to create two different orders of the composition, given this f of x and this g of x. We want to find g circle f and f circle g. I'm going to cut the page into halves. So first one, g circle f, which is g evaluated at f. And the second one, f circle g, which is f evaluated at g. Okay. So g of x is the square root of x plus 2. G of f then is going to be the square root of f plus 2. Now I'm going to replace f by its function, square root of x squared minus 3 plus 2. Now believe it or not, that's as far as we can go. That's as fully simplified as it gets. Square root of a plus b does not equal root a plus root b. That's the same for minus. The square root of a minus b does not equal the root of a minus the root of b. So does not simplify. That same rule is what prevents us from bringing the 2 into the square root as well. We can't bring it in. Okay, next example. It's the reverse order. We're plugging g of x into f of x. So I'm going to start by writing f of x. F of x is x squared minus 3. Now I'm going to plug g into it. F of g is g squared minus 3, only replacing the x's by g, not the 3 by g. Okay, now what is g? Well, g is the root of x plus 2, so I'm going to plug that in. Root x plus 2 all squared minus 3. This one requires some more work. We can actually FOIL out x, the square root of x plus 2 all squared. We can FOIL it. So root x plus 2 times root x plus 2 minus 3. I had some mean teachers in high school that would take off marks for not having equal signs line up. So now I purposefully will make them not line up. Go out of my way, even when it's possible, I won't line them up. Okay, so FOIL, first times first, root x times root x, plus outside times outside, 2 root x, plus inside times inside, another 2 root x, plus 2 times 2, 4, and then the minus 3 that was hanging out watching the FOIL. It's still there, we still have to take care of it. Okay, next step, root x times root x, like root of 25 times root of 25 is 5 times 5, which is 25. Root of 4 times root of 4 is 2 times 2, which is 4. Root of a times root of a is going to be a. So x plus, we can combine the next two. They're like terms. There's 2 root x's, another 2 root x's, so there's 4 of those, 4 root x. And the last two pieces are like terms. They're both constants. 4 minus 3, we get 1. So notice that this is not the same. G circle f and f circle g are different, which is usually what will happen. Okay, next expression, we want to do both compositions. We'll do both orders, so I'll split the slide. Part A, we'll do g circle f, which is g evaluated at f. Part B, we'll do f circle g, which is f evaluated at g. Okay, and then the starting point, like I'm writing extra steps, and the reason I'm writing the extra steps is that it's less likely you'll make a mistake if you write things out this way. So begin by writing g of x. Even though it's there, write it down anyway. X squared plus x. Now write g of f, because since you're plugging f of x into g of x, just start by plugging the letter in. So f squared plus f, replacing all the x's by f's. Now I'm going to replace all the f's by whatever f of x is. In this case, it's x squared plus 2, all squared, plus x squared plus 2. Okay, and now we can do the FOIL. So remember, something squared is that bracket times itself. that thing times itself. So we have x squared plus 2 times x squared plus 2. We do the full FOIL, and we will get x to the power of 4 plus 4x to the power of 2 plus 4 plus the x squared plus the 2. And now we can combine like terms. There's only one piece that has x to the power of 4, so it does not combine with anything. We have a 4 times x to the power of 2 and a 1 times x to the power of 2. We can put those together as 5 times x to the power of 2. And then we have a 4 plus a 2, which is a 6. That's our final answer. Next one, f circle g. So I'm going to say f of x is x squared plus 2. F of g is g squared plus 2. Now I'm going to replace g by its function, which is x squared plus x. And I don't replace the 2, because 2 is a constant. You don't replace it by stuff you plug in. Okay, now I'm going to do the FOIL, and this time I'll write it out, since it's weird. X squared plus x times x squared plus x plus the 2. Now we FOIL. X squared times x squared is x to the power of 4. X squared times x is x to the power of 3. Inside times inside, x to the power of 3 as well. And last times last, x squared. Now there's one more step, which is to combine like terms. There's only one power 4. There's two terms with power 3, so 1 times x to the 3. Another 1 times x to the power of 3 is 2x to the 3. There's a single x to the power of 2, and then a plus 2. So that'd be the answer for that one. And again, notice that they are different. Okay. Next example. Again, two different orders of composition. Do each of them separately. Question A, G circle F is G evaluated at F. Question B, F circle G is F evaluated at G. So start with G of X. In this case, it's x squared minus 4x plus 4. So what's G evaluated at F? That will be F squared minus 4f plus 4. Now let's plug in what f of x is. So square root of x plus 2 all squared minus 4 times the square root of x plus 2 plus only 4. And we'll do the FOIL. So root x plus 2 times root x plus 2, we'll get a root x times root x, which is x. We'll get a 2 root x and another 2 root x, so 4 root x. And then a 2 times a 2, so a 4. The next piece, we're multiplying that 4 into the bracket, so all the parts get hit by it. So 4 root x subtracted, and the minus 4 hits the 2 as well, so minus 8, and then a plus 4. Next, combine like terms. We have some stuff that cancels. A positive 4 root x cancels a negative 4 root x. We have a negative 4. Sorry, we have a positive 4, another positive 4, which is 8, and a negative 8, which cancels to 0. We're only left with an x. Interesting. Part B, opposite order. So I'll start by writing f of x is the square root of x plus 2. We're plugging g into it, so we want f of g, which is the square root of g plus 2, which is the square root of x squared minus 4x plus 4. There's absolutely nothing wrong with this answer. This is correct. We can declare victory. We did what was requested of us. But look at that quadratic. Can you factor it? You might ask, you might be saying, well, if I could factor it, so what? I mean, okay, I'm going to factor it, and then I have the square root of 2 factors plus 2. Well, let's see what those factors are. Maybe something nice will happen. So I'll put 2 brackets in here, leading each bracket with an x. I'll use the product and sum method. I want two numbers that multiply together to give me positive 4 and add together to give me negative 4. And the answer is going to be negative 2 and negative 2. So I have x minus 2 times x minus 2, which is x minus 2 squared. The square root of x minus 2 all squared plus 2. Now what? Okay, well, just a little comment here. What's the square root of 5 squared? So 5 squared is 25. The square root of 25 is 5. What's the square root of 10 squared? 10 squared is 100. The square root of 100 is 10. What's the square root of 7 squared? 7 squared is 49. Square root of 49 is 7. So what's the square root of x minus 2 all squared? It's just going to be x minus 2. It's actually the absolute value of x minus 2, but let's not be too picky today. Absolute value because it can't possibly be negative. When you square something, it's going to make it positive. So if you plug in, let's say 1 for x into the x minus 2 piece, you're going to have 1 minus 2, which is negative 1. If you square it, it becomes positive 1. Take the square root, you get positive 1 again. Whereas if you plug it in now, you're going to get 1 minus 2, which is negative 1, not positive 1. So we've got to be a little bit careful with our domain. What I just wrote is true for x larger than and equal to 2. But let's keep going. Let's not be picky. We got x again. I won't even write it down. I'll just pretend I didn't say that. So the first one's equal to x, the second one's equal to x. The reason this is happening is that these two functions have a special type of relationship with each other. And before I tell you what that relationship is, let's think about what this result means for each of them. G of f of x, I'm taking a machine f of x and plugging the output of that machine into g of x. X is the input I put into the first machine. So I'm putting, let's say, I'm putting $1. Oh, I'm old. I'm putting $2 into a pop machine, and that pop machine spits out the pop can into another machine. And that machine does something mysterious, and my $2 comes out. It's like an anti-pop machine. You give it pop and it gives you money. So these two machines, this f of x and this g of x, are opposites of each other. Whatever one does, the other one's doing the opposite. So one of them slices apples, the other one glues apples together. And that analogy with the apples doesn't make sense, because that's not quite an opposite machine. You can't run it. You can't run it in both directions. You can't start with an apple, glue them together, and then I guess you can. You can glue some apples together, and the machine will just slice them where they're glued and make apples, I suppose. But anyway, so that's what's happening here. These are opposite machines. The fancy name that is used for this is that these are inverse functions. They're the inverses of each other, which is not part of the course. So you will not be asked to construct inverse functions, but I'm mentioning it here because some of you are going to be taking Calculus 1000, and in that class you'll start the term, like on day 2, you'll be talking about inverse functions. Maybe day 1, depending on the prof. So I thought, hey, it's useful to talk about it at least a little bit here. We'll continue with the next topic for this section in the next video.